The dynamical systems that seem to exhibit chaos, it's usually very hard to prove that what you're looking at is actually mathematically, rigorously chaotic dynamics, meaning that all orbits are hyperbolic and unstable and there's exponentially many of them as a function of time. I use this very simple example cooked up by a chemist called Roessler, but he's a classically educated man, very impressive. And he wrote some equation trying to understand Lorentz dynamics, which said that if you take an interval on the attracting set of those equations, that interval gets stretched, and then as it goes in its merry way, it starts getting folded, it starts getting squashed, and it comes back in something that seems to be a line, but it's actually several Fermis thick if the original interval was a centimeter long. So that's Roessler flow, and it's very easy to simulate. And the main beautiful thing about it is that first, if one does Poincaré section, and at the moment I'm in a state of shock because I've just been informed by reliable sources that nobody understands why I'm teaching you Poincaré sections. So there we are. Poincaré section is something that looks pretty boring. In this case, if you take this Poincaré section, but it's three-dimensional for a Poincaré section, it's two-dimensional plane, and the flow seems to live on the line, so we look at the return map. And one finds out that this return map, which is the map if you measure the distance, curvilinear distance here, from the fixed point and along its unstable manifold until it folds back into itself. This is this point. It turns out that that's a very pretty map, which you can understand in great detail. Looks something like that. And it turns out that when you think about it, if you understand solutions dynamics on this map, you understand it in full state space, because any point here in this map, it's actually embedded in a two-dimensional plane, which is embedded in 3 dimensions. So you have full information. So this is not one-dimensional map in the sense that every point here, you can go back all the way here and discover that that point is right here. So if I'm at point X of S, if I'm here, point X of S, then I actually have all coordinates of this thing. Now the reason why this is sweet is that it turns out that when we look at fluttering flame front or we look at Navier-Stokes equations, the same kind of thing happens. This is 1 million coordinates or 64 or 10,000. But if we find a nice Poincaré section, which is small in some sense, this is extreme case, it looks like a line, then we can study dynamics there and we can go back and forth the full space and we can predict existence of trajectories. It's very easy to understand here, and they're very hard to understand in the original problem, because in the original problem they do something. Here it's not very complicated because there isn't much they can do, but they go around and they do something before they come back, for example, if there are periodic points. So if you can find them here, we can go back and we can go back and we can go forth. And it costs you nothing but thinking, because this is all easy to compute. It's not a horrible thing.